All right, looks like we are all here. So I think it is time to start. Hope everyone is staying safe at home. And let's begin. All right. So in the last couple of lectures, we've been talking about this idea of propositions as types. So specifically, what that means, this idea that you can have a program that both computes some value and also produces not just that value as output, but also some proof about that value. And last time we talked about how we can look at ordinary data types like the natural numbers or integers or lists or trees in the same vein. So we wrote down these introduction rules for the natural numbers, often almost as if it was some kind of proposition that we wanted to prove, except of course we're not proving the natural numbers, we're instead writing down sets of values. So we wrote down these introduction rules, and we talked about how from that introduction rule, you could actually pull out some kind of, you can automatically generate this kind of induction rule. And that induction rule, actually, that corresponds to this idea of doing, writing down a recursive function, a function that recurses over some value. And so we talked about how we can recurse over a value, both to compute some new value, but also to build some proof about that value. And we did that with this example of proving that 0 is less than or equal to n by recursing over n. I call this proof by recursion, but since, as we talked earlier, recursion and induction, they're really sort of one and the same. When we're done a recursive definition, you can rewrite that as invoking the induction rule for your data type. But of course, there's that proof by recursion, and proof by is really proof by induction here. So now I want to talk about the last part of our series on dependent types. And in particular, what I'd like to look into is this idea of type dependency, and specifically this idea of defining properties of values via inductive data types. So we'll talk about that. We'll talk about how that's kind of like writing down a trace of some computation of that determines the property. And then we'll talk specifically about how an inductively defined property, its values will be proofs of that property, and what it would mean to induct over those proof terms. So we'll talk about how assumptions, which are these inductively defined properties, allow us to learn something about the values they are about. And then finally, we'll talk, we'll sort of finish up the series by specifically talking about this idea of proof carrying code, about code that incorporates both values and proofs about those values. We'll talk about subset types and data structures that mix the idea, different pieces of code and data, but also proofs and properties. So that's sort of what we want to do today. And where I want to start is by talking about inductive predicates. So recall a couple of lectures ago, we talked about how you write down introduction rules for different propositions that you may want to prove. And then that's the core of how we construct proofs. So we found that specifically this idea of writing down introduction rules is related to this inductive types idea, where you write down the constructors from which a data type is defined. And in the last lecture, we did this, constructor-based type definition, specifically to write down definitions of different kinds of values your program might compute over, like numbers or lists or trees or that kind of thing. But now I want to think about how these data types that we've written down correspond to proofs and properties. Because recall, one thing that we've been discovering throughout this series of lectures is that types that your program computes over, like pairs or functions, they correspond somehow to proofs of various logical properties. Things like functions corresponding to implications and pairs corresponding to conjunctions. So I want to take this definition that we've written down here of the natural numbers and just try to turn it into something less data typey and more proposition-y. And so what I'm looking at here is I want to try to inductively define not value types, but propositions and their proofs. And so here's one proposition that I can think of. This is a proposition about numbers. So it's kind of natural to write down in this style, and we're already talking about numbers. And this is the idea of a number being even. So the way I've written down, I've said that 0 is an even number, and also that evenness kind of is maintained if you increment by 2. And if we go back a slide to look at the definition of the natural numbers, you'll see something quite similar, except when we were talking about the natural numbers, of course, we said that 0 is a value of type nat, and then incrementing by 1 produces a value of type nat. But here I am instead talking about a property of natural numbers. So it's not that 0 is a value of type even. There's no such thing as a type even. There's only the type 0 is even. And when I say type, of course, you really want to think proposition. So here I've introduced these two constructors for 0 being even. And the way I chose these constructors, well, we'll get back to that in a moment, but you can see that because of how I chose them, they correspond to our notion of evenness, namely that it's some number of increments by 2 up from 0. So let me give you another case in which you've seen this sort of induction definition being used. And that's in the programming language semantics that you saw earlier in this course. Remember that when we were talking about programming language statements and how they execute, we used this notation where you had a statement and then an arrow and then another statement. Well, one way you can think of this notation is as a proposition that this statement 1 steps to statement 2, that it's valid for the program to execute statement 1 by reducing it to statement 2. And so what you had at the bottom of the line here, that was some kind of proposition. And that proposition, like in the case of sequencing, might rely on certain assumptions. So for example, when we talked about programming language semantics earlier, I said that I read this as S then T evaluates by first evaluating S. But you can also think about this as answering the reverse question: how would you prove that S then T evaluates to S prime then T? And the answer is that you would have to show that S evaluates to S prime. And so again, you can think of the programming language semantics we did before as also a form of inductively defined propositions. Propositions that we define by talking about all the different ways in which you can show that they are true. Much like the case with even numbers a moment ago. So so any questions about this idea of inductively defining not just new data types, but also new propositions? And I guess let me draw a little analogy between what we're defining here via these constructors and the actual proposition being proved. Think about our definition of even numbers. We said that I'm defining evenness by saying that 0 is even and that adding 2 to an even number keeps it even. Well, compare that to the code you would write to check if a number is even. This is maybe weird code because what you'd probably write is something like n%2 equals 0. But this is some code you could write to check if a number is even. You first check if it's 0. In that case, return true. Otherwise, you check that n minus 2 is even. In that case, you return true. And otherwise, you return false. Now, this code isn't ideal. For example, it'll run forever instead of ever actually returning false. But it does reflect something of our understanding of what evenness means. This, even if it doesn't actually work as a piece of code, is kind of close to code that might work. So you can see here that each of the branches of the if statement correspond to one of the constructors. So when I say if n equals 0, return true, what I really mean is that there is a constructor of even 0. And when I write here that if even n minus 2 return true, you can think of that as being the correspondence between n and n plus 2, except I've inverted it here in the code. And as a result, I'm saying that there ought to be a constructor of n plus 2 even. That's what the return true means. And furthermore, that in order to know that, you must first check that n is even. So you can think of what's going on above the line as part of the path condition of the code, like we talked about a couple of months ago, and each of the branches of this code as corresponding to a different way in which you can conclude that a certain number is even. And of course, we do have this else condition, and that corresponds to this general notion that there isn't any other way of proving even. There isn't any other value whose type is one of these inductive types except by applying one of the constructors in question. And so in fact, if you look at a particular term, a particular proof that some number is even, like for example, if we consider what is the proof term you would write to show that the number 6 is even? Well, 6 isn't 0, so this one won't apply. So you have to use this term. 6 is something plus 2, more precisely 4 plus 2. So let's give little names to each of these constructors that we'll apply. And because 6 isn't equal to 0, we have to look at this EV2. So our proof that 6 is even would begin with EV2. And now we'd need a proof here that 4 is even, because 6 is 4 plus 2. So to construct a proof that 4 is even, again, you check there's no 4 isn't 0, so this one won't apply. So you need to apply this one. So we're going to have another EV2, and I'm imagining sort of a big parenthesis over here. And EV2 has to be applied to an argument. And the argument in this case is going to have to be that, well, if 4 is n plus 2, then n has to be 2. So it has to be a proof that 2 is even. So again, our proof that 2 is even will itself use EV2. And then finally, we're looking to prove that 0 is even. And in this case, EV0 in particular will apply. So this is kind of the proof term that you'd write down, that 6 is even. And if you think about this piece of code that sort of corresponds to these constructors we wrote down, then you can think of our proof term as being kind of like a trace through the execution of this program. It's telling us that if you ran this function even with an argument of 6, it would first go down this branch, and then it would go down this branch again, and then it would go down this branch again, and then finally it would go down this branch, and that's why it would return true. And with this correspondence, hopefully you can see a few things. First of all, why this notation for writing down proofs of properties makes sense. In effect, we're just writing down a guide to the execution of the program that determines if that fact is true or not. But it also hints at how this is a little stronger than just writing down a program that returns true or false. Because since this only records a concrete execution that eventually returned true, it's sort of okay that our program infinite loops in some cases. Because we're only ever dealing with a concrete proof term. We're not trying to decide whether or not a given number is even. And luckily, you can decide if a given number is even, but there are other properties you can't immediately decide, like, is a certain number the product of two primes? That's difficult to decide on a computer, but it's something that you could write down a compelling short proof of. And even if you had an algorithm, you can convert it into a proof in this form just by saying, just by writing down a trace of how that algorithm comes to its conclusion. So the overall upshot here is that our technique of defining new propositions using their constructors, that technique is fundamentally, in a sense, about writing down a trace of the individual facts you looked at to come to a certain conclusion. In this case, to come to the conclusion that 6 is an even number. So let me now take this sort of idea that we've talked about and try to bring it to life in an actual text editor with Lean so that you have a sense of how this works. So I'm going to open up my my Lean file, and somewhere over here is a button that opens up that goal on the right hand side, and I'm going to define this notion of evenness. So just as last time when we defined natural numbers with the keyword inductive, I'm again going to use the keyword inductive, but this time to define a proposition, not to define a value. So my proposition will be called even. And unlike before, where we wrote something like this, we're now going to say that it is not a type, but a function from natural numbers to types. And that makes sense because even isn't a proposition. 2 is even is a proposition. So there's an argument that you have to pass to even before it becomes a thing you can prove or disprove. And now I'm going to write down those two constructors in the same form that I had them here, and I'll keep calling them EV0 and EV2. So first, let's do the EV0 constructor. And so for that, I write down EV0, which is a proof that 0 is even. And then I'm going to write down this EV2 proof. So what I'm going to write here is that EV2, it works for all natural numbers n, and it assumes that n is even, and it results in a proof that n plus 2 is even. And so you can see that this, again, is what goes on above the line, and this is what you see below the line. And this is quite analogous to the definition of natural numbers that we had last time, where you did something like except you can see that unlike with, oh, I guess this should be my net. Unlike the definition of natural numbers here, even has this additional parameter. It's really defining a function that takes a natural number. So I have to annotate each call to even with those parameters. And then once I have this definition, I can write down terms. So for example, I can write down EV2 of EV2 of EV2 of EV0. And you can see that that is actually a proof that 0 plus 2 plus 2 plus 2 is an even number. And this is a weird way of writing it, but Lean knows that that's actually 6. Questions? And actually, I know that a question that came up last time was what these underscores are for. And that's just because the way that I've written this down, EV2 actually takes 2 arguments, one of which is n, and one of which is a proof that n is even. And so with this underscore, I'm asking Lean to do the hard work of typing out the actual numbers each of these refer to, which I guess would be 0, 2, and 4. So questions about this idea of writing down a proposition, a fact that we might want to prove via this inductive type by writing down its introduction rules and thinking of that kind of as a set of proof terms that you can now write down. Nope, none. Okay, that's guess it's getting toward the end of the quarter. Everyone's just calling it in. All right, that's fine. So what we've got so far is we've got an inductive data type defined, and I want to work through a couple of these so you sort of get the sense of what's going on. So let's define another one, and in this case, what I want to write down is this sort of more realistic computer science notion like evenness. How often is that a problem? Let's write down this more realistic notion of a tree being a binary search tree. So first we need to define what a tree is, and I'm going to do it like this. I'm going to say that a tree, I'm just going to make it a tree of natural numbers to keep things easy. It's either a leaf node, which contains a natural number inside, or it is a branch node, in which case it has 2 leaves. Oh, you can't write that down. It has 2 trees on the left and the right. So we can write down trees like we can, for example, write down branch of leaf 2, leaf 3, leaf 5. And that results in a tree, as you can see here. And by the way, I should note this open stuff just means that I don't have to write tree.branch each time. There's nothing else to it. So now that we've written down this definition of trees, let's try to write down the proposition that trees are binary search trees. And so let's figure out what that is. So it's going to be a predicate that I'm going to write down as BST, and it's going to be a predicate about trees. So here I'm going to write down tree to type, as in BST of T is a proposition. T being a binary search tree is a proposition, but of course, binary search tree in general is not a proposition. So what makes something a binary search tree? Well, the basic idea when you have a binary search tree is that all the values in your left child have to be less than or equal to all the values in the right child. So we're going to need to track kind of like what's the biggest, what's the smallest value in a tree. So I'm actually going to take this proposition that I've called BST, and I'm going to add 2 additional things that we're going to track about this tree. We're going to say that it's a binary search tree, that this tree is a binary search tree, and its smallest element is this, and its biggest element is this. And so the first thing that I want to have is the first thing that I can easily describe these least and greatest elements for is a leaf node. So what I want to say is that a leaf node containing n is a binary search tree with the smallest value n and the biggest value n. And I guess I need to add for all n over here. So that's one way that a tree can be a binary search tree. We can say that it's just a leaf node. Leaf nodes are always binary search trees. The other thing that it could be, a tree could be a branch node. So let's think about how a branch node can be a binary search tree. And there's going to be a lot of variables involved. Well, let me just introduce them as I go. So to be a binary search tree, if you are a branch node, what do I need to know? Well, first of all, I need to know that T1 and T2 are themselves binary search trees. And second of all, I need to know that the biggest value in T1 is less than or equal to the smallest value in T2. And so let's actually name those biggest and smallest values. So here I've said that T1 is a binary search tree with smallest value A and biggest value B. T2 is a binary search tree with smallest value C and biggest value D. And I'm going to require that B is less than or equal to C in order for this to be a binary search tree. So Lean is a little unhappy that I've invented all these variable names without telling him about it. So we've done that. And then finally, since we're annotating, since our binary search tree predicate now includes information about least and greatest elements, I'm going to have to add that information here as well. So the least element in this one bigger tree that combines T1 and T2 is going to be the least element in the left tree, and the biggest element is going to be the biggest element in the right tree. And so here I've defined this binary search tree prime predicate. And let's just go ahead and prove that T1 is a binary search tree. So I'm going to have my proof. And what I'd like to write down is that BST prime of T1. Except, of course, I can't just write down BST prime. I also need to know the least and the greatest element. So I happen to know those. I can say that T1 is a tree that is a binary search tree and has least element 2 and greatest element 5. And the way I'm going to prove that is to say, well, first of all, T1 is a branch node right here. So that's the first thing I'm going to have to write down. I'm going to have to write down BST prime dot branch. And BST prime dot branch has a bunch of arguments. So I'm going to need to write down a proof that its left child is a binary search tree, its right child is a binary search tree, and this less than or equal to relationship. So let's call those proof 1 and proof 2 and leave that last bit alone for now. So I'm going to first define proof 1, which is going to be a proof that, so proof 1 is going to be a proof that this left-hand child is a binary search tree. And I'll do that again with branch because the tree starts with a branch node. And I'm just going to name 2 proofs right there. I'll get back to them in a moment. The other thing we have is proof 2, and this is a proof that the right child of T1, namely this leaf node, is a binary search tree. And for that, I will use BST prime dot leaf. And now we need to do the same thing for proof 1A and 1B, and both of those are proofs that a leaf node is a binary search tree. So both of those will use BST.leaf. These also need underscores, annoyingly, I guess. So we're almost done, but we have this weird underscore. Z3 is asking, I see. Annoyingly, I'd otherwise need to state all these values. I'm going to use these curly braces, which will make that go away. So Lena is now asking us to prove this last part of the constructor for a binary search tree. It's asking us to prove that 2 is less than or equal to 3. And Lean actually has this weird hack to do that. If you write down dec trivial, Lean goes and checks for itself whether perhaps 2 is less than or equal to 3, so you don't have to write it down yourself. And we can do the same thing here. And I think it will work. Maybe not. This needs, there we go. So what we've got here is a proof that this tree that I've written down is a binary search tree. And you can see that to write down that proof, we basically reflect the actual structure of the tree in the structure of the proof terms. We've got this BST prime dot branch at the top, and then we have BST prime dot leaf for all of the leaves. And that makes sense because the way you would check that a particular tree is a binary search tree is by recursively descending down the tree and keeping track of the biggest and smallest elements in that tree. So that's we can write down a proof like this. And now, of course, at the top level, you probably don't actually care what is the least and biggest element of your tree. So you can also define something like BST, which is just a tree to type. And you define that by saying that just there exists some A and B such that BST prime, it's a BST prime T A B. Oh, sorry. For weird reasons, we need to write there exists that way. Okay, so questions about this idea of, first of all, writing down inductive predicates. Second of all, this idea of writing down proofs of inductive predicates. And possibly in the context of this more interesting and more realistic example, where we're talking about the size of a binary search tree. Go ahead, Bradley.
Could you write branch and leaf constructors that return a proof that the thing you've constructed is a BST so that you can only write down BSTs?
We can, and we'll get back to that toward the end of the lecture. So just hold on to your virtual hat.
Cool.
Other questions? Okay, in that case, I'm gonna attempt to make use of the Zoom wizardry that I discovered last time of putting y'all in break rooms. So I'm gonna ask you to write down the constructors for a new inductive predicate. And this inductive predicate is gonna be called has length. So what I want is an inductive predicate called has length, which takes a list of natural numbers and a natural number and tells you whether this list L has this length N. So looking for, we'll give you a hint, there's two constructors to this proposition. So I'm gonna give you 30 seconds to think about it, and then I'll put you in some breakout rooms to discuss. Okay, so I hope you've had a moment to think about it on your own. And now I'm gonna break you all into some breakout rooms. So let's see what happens. Please just discuss what you came up with for some constructors for this inductive predicate that a list has a certain type. Okay, so we've come back together. So I'll wait for people to exit their breakout rooms. I'm sort of confused about the whole breakout room process, but we'll figure it out. All right, so while people are filtering back in, who had some ideas for how they would define the has length predicate? Okay, Skylar, I already heard your idea, unfortunately, like moments ago. So I'm gonna see if anyone else has another idea. Well, I mean, possibly the same idea, but if anyone else has an idea. Go ahead, Oliver.
Maybe I'll give a base case and someone else can do the inductive case. But I think that the empty list is a unique entity. So the base case can be you have the empty list, and it has length 0.
All right, cool. So we're gonna have a base case, and I'll just call it base. Maybe I'll call it Oliver,
Okay.
which says that the empty list has length 0. That sounds pretty good. That at least sounds true to me of lengths. What about the other constructors? So far, this only ever allows us to prove that the empty list has a certain length. What other lists have length? How do we prove that another list has a length? Go ahead, Calvin.
So you could combine the constructors for both the natural numbers and like the lists. You could say like cons and successor.
I'm not sure what you mean. You mean something like
has length cons like a head dualist.
Okay, I think you write that this way in lean.
And then you have like the successor number like n+1.
Okay.
And then
so, and I'll do the usual ALN here.
And then you would say has length for L and N.
Okay, cool. So perfect. So in other words, we're saying that a list that contains an element that's a head element plus some other stuff that has one more than the length of that other stuff, which makes sense because we just added a term onto the front. Or here's a different way to think about it. So this is a great definition. And here's a different way we can think about the same thing. If you were to define a length function from, say, list of natural numbers to natural numbers, you'd probably define it like this. Length L+1. I hope y'all can see that the Zoom stuff covers the bottom of the screen for me, but I think you can still see it. So if you were to look at this definition of length, you can see that it has some obvious similarities to this definition of length. Here, has length is saying that has length applied to a cons, which is like length applied to a cons. That results in a recursive call. So that's our input, which is recursive. And we add +1 to the result. So this is one way of defining has length, and it's sort of naturally related to this way of defining length, which might seem a little weird because this is obviously a better way of defining length, but it has some advantages like we've seen even in the case of evenness, where we don't have to worry, for example, about termination and so on, and more so for other things where you can basically write down you can have a precondition here that is difficult to check. There's certainly nothing stopping you from writing down a Turing machine halts as a inductively defined proposition. It just means you won't always be able to prove it, but you couldn't write down a program that checked that property. Yeah, go ahead, Oliver.
I had a quick question. So we wrote it as for all A, L, and N, and then we proved a property about A cons L, right?
Yep.
Is it also valid to write it as for all L, N and deconstruct it into the first item and the rest, or does that not work?
So you're saying something like, you know, match L with has length sorry, I got the syntax wrong here.
Yeah, that's exactly right.
Yeah, so you can see how this is getting a little weird. Like, what do I stick into here?
Yeah.
I mean, I guess this, but how's that related to L?
Gotcha.
L, I guess, over here, and like, what is N?
I would do
is that
like L
has...
N minus 1.
Yeah, and
Minus 1.
you can see how this
Does
is
that not
getting a
work?
little weird.
Yeah, it gets a little weird. That's why I was wondering if it works or not.
So it doesn't. And the reason
Okay.
is that what you've got here is a computation. It's a
Yes.
value, not
Okay.
a proposition. This is actually, well,
Well,
okay, this won't work. There's probably some kind of way to rescue it.
Okay.
But no one does that because it's weird.
No one does it.
I'd be happy to explore this a little more. I don't think this, which I've just written down, actually makes any sense. Like, I don't think this would do what you want it to do.
Yeah.
And Lean seems unhappy about it as well. But,
Gotcha.
well, okay, some of why it's unhappy is that. But definitely Lean is a little unhappy about this. And I'm not totally sure it could be rescued, maybe, but yeah, you wouldn't do this way normally.
You wouldn't do it that way.
I sort of like to think about these as kind of being that trace of why you made this decision.
Okay.
So in this case, you decided that this list has this length because you already knew that its tail had that length.
Is there some property like every list is either cons or empty that you can use in these sort of proofs, or is it not usually go that direction?
Yeah, so I mean, right, the way that list is defined is specifically by giving its constructors, and here they are. Every list is either empty or it is cons.
Gotcha.
And we're not making use of that property here. If there were some kind of hypothetical other sort of list, like a cons, but it's red for some reason, that's sort of a little joke, sorry. If there were some other constructor of lists, we would just be unable to prove has length about it. It's an interesting fact whether or not we can always prove has length for some number, for any given list, and which is called decidability. So that's where that plays in. So you would make use of the fact that there are only two kinds of lists if you wanted to prove decidability, but that's not actually important for writing down has length.
Okay, thank you.
Any other questions about writing down inductively defined predicates? All right. In that case, let's move on. So we've now talked about writing down predicates as this sort of inductively defined thing, and now I want to talk about how you would use those values if you were handed one. We've already talked about how you'd write a new one down. So we've now inductively defined propositions, and as you'll recall from like way back, if you have a type that you've defined via its constructors, like the proposition n is even, then that generates the elimination rule, or what we call an induction principle. And We went over how you do this last time, but basically for each constructor, you kind of have a different one of these. You have a different one of these arguments on the left and the right. So for the 0 constructor, you have this p of 0. For the n+2 constructor, you have this p of n+2. And then for each of these p of somethings, you have a, this n even becomes a p of n implies, and that somehow together that pulls together to make this induction principle. And what's interesting is that before we had just nat here, and that allowed us to increment by 1. But because we know that n is even, we know that we can actually step by 2 because even numbers kind of increment 2 at a time. So what we have is we have a proposition and a way to use values of that proposition's type. In other words, proofs of that proposition. So let me give you an example of how you might use those proof values and this induction principle to do some kind of computation or to write down some kind of proof. Except before I do that, I see that Calvin has a question.
Oh, I left my hand up. Sorry, I'm putting it down.
Oh, okay. Yeah, that's fine. I might get confused if that happens.
I was just stretching.
Yes. Stretching. Okay, good. It's good to all remember how to put our hands up. What's this induction principle basically doing? It's saying if we have a proposition about n and we know that n is even, well, we can do this inductive step. And in this inductive step, we have to prove the proposition about some other value n, a value of n too smaller than before. And as we saw last time, Lean is going to automatically generate inductive principles like this. So if we go up here in the file to our definition of even, we can ask even.rec, and I'll do it with the @ sign. And then just like we did last time, we can take this and somewhat clean it up by splitting it onto multiple lines, and then changing this p to a for all and removing some of the type annotations because we understand them ourselves. And if you take a look at what's going on here, you see that we have this property, which I've always called P, but Lean really likes C. It says that if C is true of 0, and if C being true of n implies that it is true about n+2, then it is true about all natural numbers n. And that's that same induction principle that I had on the slides. So how we use an induction principle like this? Well, one place where you might want to use an induction principle like this is in a proof. So for example, suppose we want to prove this pretty normal theorem about even numbers, which is that if you add 2 even numbers, you get an even number out. Now, last time we talked about how you can prove theorems like this by recursing over some of these values like n and m. But if we try to do that here, it won't work. So suppose we do an induction over m, but you'll get something similar if you try to induct over n as well. Well, if you try to do an induction over m, then you're going to get 2 cases corresponding to the 2 cases of the induction, right? You're going to have one case for the base case of the induction for m is equal to 0, and another for the inductive case, which is that m is equal to m prime plus 1. So here's what that base case and the inductive case will look like. And this top case, that does look pretty useful. It's asking if n is n even. That, that looks like a step forward. We could prove that. But in this inductive case, when we do the induction, we get this additional, we're saying if n is even and m plus 1 is even, is n plus m plus 1 even? And to help us prove that, we get access to this inductive hypothesis, which says if m is even, then n plus m is even. The problem is that this is kind of useless. If m plus 1 is even, we definitely know that m itself is not even, because if something's even, that thing plus 1 isn't even. So this inductive hypothesis that we get, this additional thing that we have access to when we prove this fact, totally doesn't help at all, because we can never prove the assumptions of that implication. Alternatively, we can never call that function. So inducting over to the natural number m here won't be useful. And that makes sense, because inducting over m basically means going over m one step at a time. But if we go one step at a time down from m, then we won't be able to make use of the fact that m is even, because that involves going 2 steps at a time. So instead, what we want to do is induct over the proof that m is even. Recall that there are 2 ways such a proof could exist. So if we do induction, we have to have one subproof for each of those cases. The first subproof is that if m even refers to the standard proof that 0 is even, that EV0 constructor, then we just need to prove this, that if n is even, n plus 0 is even. And note that when I wrote this down, I removed this argument because we now know its concrete value. It's the EV0 constructor. And I also removed m because we now know its value. If the proof that m is even is EV0, then m must be 0. And that's why I substituted a 0 in over here. And then likewise, the inductive step now says, well, the inductive step is going to correspond to the EV2 constructor, which says that if m is even, then that m plus 2 is even if m is even. So here it's saying if m is even, if that implies that n plus m is even, then what we're dealing with now is a proof that m plus 2 is even, and we need to prove that n plus m plus 2 is even. So, okay, there's probably a little too much detail going on there, but what I want to emphasize is this idea of inducting over the proof of a certain proposition. So let me do this same example, but in lean, so you can sort of see how it boils down to actual code. I've got my definition of evenness right here, and I want to prove a theorem, which I'm going to call even add, which says for all n and m, if n is even and m is even, then n plus m is even. And I'm going to use this proof, do this proof using this same sort of underscore style, this same pipe style that you've seen before. But now what I'm going to focus on is pattern matching on this proof that m is even. So suppose that proof is EV0. Then I've actually discovered additionally that m itself must be 0, because EV0 can only prove that 0 is even. And in this case, what I have left to prove is for all n, whose proof is here, which I'm going to call PF, implies even n plus 0. So n is the same thing as n plus 0, so I'm just going to write down PF here, because that is already a proof that n is even. And now I'm going to do the same thing now for the m plus 2 case. Here I'm going to discover that m is equal to m plus 2 by virtue of discovering this proof argument to be EV2 applied to some proof prime that m prime is even. So again, what I've got going on here is I know that the proof that m is even is EV2 applied to some PF prime. That tells us that m is actually 2 more than something. And it also gives us this proof PF prime that m prime itself is even. So I'm now going to write down my, I think this is all good. Now I'm going to write down my my proof, and that proof is going to say, well, actually, hold on. Let me look at what these red underscores are like. Oh, I see. Sorry. That's that nonsense with the underscores again. My apologies. Okay. So now, so to rewind, I'm doing induction over to this proof term. It has two cases, one for EV0, one for EV2. So in this case, what I'm trying to prove is if n is even, well, I have my proof over here, PF, that n is even, and what I'm trying to prove is that even n plus m plus 2. So the way I'm going to prove that, I'm going to say, well, n plus, sorry, m prime plus 2 is 2 bigger than n plus m prime. So I'm going to apply EV2. And then I need a proof that n plus m prime is even. And I'm going to use a recursive call for that. And my recursive call is going to need a bunch of parameters. So it's going to need n and m prime. It's going to need a proof that n is even. That's going to be PF. And it's going to need a proof that m prime is even. That's going to be PF prime. And I need to name n here. And I need an underscore here. So you can see that in effect, what this proof is doing is it is recursing over one proof term and step by step computing another proof term. So we have a proof by recursion. We have an inductive proof that inducts over one proof and produces another. And this is sort of the core mechanism by which you make use of a inductive predicate like this. You can recurse over them. And the fact that we only have to write down two cases here is specifically due to the fact that we've only defined two constructors for evenness. Questions about this idea of recursing over a proof term? Okay, great. In that case, I now want to finally bring this whole 3-lecture series, maybe 4-lecture series if you count the demo, on dependent types to the promised conclusion, which is this idea of mixing values and proofs about those values in one big mess, having programs return both values and proofs. So what you've seen so far is you've seen some kind of pattern matching on proof values. So we just saw, for example, this theorem even add. And what this pattern matching does is it generally involves a function that accepts both a value and a proof about that value as an argument. And then when it does the pattern matching on the proof term also tells you something about the value term. And similarly here, pattern matching, I guess I should call this EV2, pattern matching on the proof term gives you access to information about the value term. And there's no case here where n is equal to n plus 1, but is not equal to some n plus 2, because there wouldn't be any proof term that could fill that in. So we have this idea of proofs, which is this one argument to a function, telling you something about about another argument to the function. And this is what we call type dependency. This type, even n, depends on this value n. And so elements of this type tell you something about this value. So we have this sort of idea that pattern matching on the value, that it doesn't necessarily tell you anything about the proof, but matching on the proof tells you something about the value. So what we'd like to do is we'd like to keep this value and proof sort of together at all times. We don't want to have the value, but not the proof about it, because then we wouldn't learn anything about that proof by pattern matching on the value. We want to make sure we keep this extra information around so that we always have access to it. So what that means is that we'd like to package up this value and proof together into one piece. We'd like to have like a data structure, which is a pair of n and n being even. Except as I've written this here, this doesn't actually make sense because n is a value and n even, it's not a proof, this is actually a proposition. So you can't have a pair of like a value and a type. So what we'd have is more something like this. We'd have some n, which is a natural number, and some p, which is some proof. And then we'd make that pair of n and p. And so we'd like to keep this sort of pair of value and proof together in one place. What type does this pair have? Well, in languages like Lean, we usually call this sort of type a subset type. And we have a syntax that looks something like this. So we say that it's n comma p is a natural number that is even. And of course, the values of this type, maybe you think more of as pairs. They're a pair of natural number and proof. So we can see this in Lean. I can open up here and I can say, I want a natural number n and a proof that n is even. Is this how you write this down? This how you write this down? Oh no. Folks, I think I've forgotten my Lean syntax. Yeah, it's complaining about Lean has this distinction between value types and non-value types. Sorry, folks, I have forgotten that syntax. But another way to think about this, idea of a subset type, type plus some proof about that, a value of a certain type plus a proof about that value, is to think what other logical proposition has the same structure. It proves some kind of proposition by taking a value and some proof about that value. In other words, we want some kind of n in tau and some proof of a property about n. Well, the natural logical proposition that has this structure is what we call there exists. It's an existential. An existential packages together a witness and some proof that the property applies to that witness. So in Lean, instead of the subset type syntax that I can't remember, we can actually use the somewhat more normal syntax here, where I'm writing a sigma instead of a there exists. That's just some Lean nonsense going on. But fundamentally, we're packaging together a natural number and a property of that natural number. And if we ask it to, can I do this? Nah. Well, okay. And if we want to write down a term of this type, we could say, for example, well, we're asking, does there exist an even natural number? So we could say my term, which I'll call T2, is going to have this type, and it's going to be defined as sigma.make of 0 and EV0. And so the sigma.make you can think of as being the constructor for pairs, and I'm telling it that my proof that there exist even numbers are that 0 is a number and also it is even. And here I'm giving that particular number and also the proof term that that number satisfies the property I want. So this gives us a sort of a first step into this idea of a mixed data structure, a data structure that includes both some elements that you think of as values and also some elements that you think of as proofs about those values. So subset types are one way that you could instantiate this, and they're broadly useful for, well, for example, this might be a return type from a function that searches for a certain element. So for example, index of might both return the index and also a proof that the value at that position is as expected. But there's other ways that you can make use of this idea of type dependency to write down these mixed data structures as well. So for example, earlier we wrote down this has length property. Here I called it of length. So here I've got the definition of the list data type at the top. And then I've got the definition of this of length predicate below it. But we can instead of sort of first constructing the full list and then iterating over the list to construct our proof, we can interleave these two. So instead, we can say that we can add an extra parameter to the list date to the list type tracking the length. So here I'm saying instead of that the empty list is just a list, I am specifying that it's a list of length 0. And I am specifying that adding an element onto a list also increments the length of that list. And you can see that my definition over here of list and my definition over here of list are basically the same, except they track this additional information about lengths that I didn't have before. So we can take this idea and implement that in Lean as well. So here where we had has length, we could instead say define a list prime, and list prime is going to be, I'll keep it a list of natural numbers, but it will take an additional natural number as an argument. So I will have nil, and that will be a list prime of length 0. And I'll have a cons, which is going to take a natural number and a list prime of length n and return a list prime of length n plus 1 with a for all n here. And so this defines something like something quite similar to has length, but you can see it contains both the parts of the list that are data, as well as somehow the parts of the list that involve a proof about its length, or at least some measurement of its length. So questions about this idea of mixed data structures that include both reasoning about data and something about proofs? In that case, I can get back to Bradley's question from a little while back, which is just to circle back to this definition I made here of a binary search tree. And here, this binary search tree, we thought of as some property of a natural number. But actually, instead of thinking of the binary search tree as a proof that sits alongside the tree itself, you've already seen that the structure of the binary search tree is basically identical to the structure of the tree itself. So let's just treat the binary search tree as the data structure itself. Instead of taking a tree as an argument, we say that, well, the leaf node just takes a natural number, and it's a binary search tree with minimum and maximum values of that number. And instead of a binary search tree branch as having two subtrees, we just say that it has two arguments, which are themselves trees, and also a proof term, and that produces a tree on its own. And now we can actually define T2 to be the same tree that I defined earlier, but automatically including information So I'm defining, I've got T2 over here, which is a branch of leaf 2 and leaf 3. And I'm defining T2 to be the same as T1. So here it has a branch and a leaf 2 and a leaf 3. And this should be BST prime dot leaf 5. And here I've left these little underscores to correspond with the fact that there's that I need some additional proof of one thing being less than another. And I think Lean should be able to fill that in on its own with this magic incantation. There we go. Okay, so any further questions about this idea of type dependency, this notion of data types that both mix data and proofs about them, and this broader dependent types approach to verifying programs? Anything else that you'd like me to do here in Lean? Skylar?
I'm a little lost as to where this ties into a program. Like, it feels like we have this thing that can basically be used to like prove facts and maybe even facts about a program, but I'm not quite seeing the connection between like this and a body of code necessarily.
Great question. So suppose that you are actually writing a program and you're implementing a binary search tree as a data structure, for example, for sorting or efficient searching or something. One way that you could write that, like in Daphne, you'd probably write that, and this is going to be some weird sort of Lean Daphne mixed syntax, but you'd write something like, you know, BST insert, and it would take a tree and it would produce a tree, and then you'd say like, you know, in Daphne you'd have some kind of like requires BST of T. I know I misspelled requires, but also this isn't valid syntax to begin with. So let's just let it lie. So if you were to do this in something like Daphne, you'd have this precondition that that you would sort of expect the caller to prove on the side to ensure that the tree it's constructed is a binary search tree. And you could do something like that in Lean as well if you wanted. You could say that it's you need a BST insert takes a tree, and it also takes a proof that that tree is a binary search tree. And maybe it would produce a tree, and then you'd have a separate theorem, which is that BST insert of T PF is always itself a binary search tree. But you can see that this leads us to kind of have this like duplicate structure where we first write functions and then we separately write down theorems about those functions. And often those theorems work in a very similar way to the function itself. So, you know, this theorem, well, this function itself would be recursive, and then we'd have some kind of like post condition, and we'd prove like a loop invariant style thing about that post condition. But instead of doing all of this where we have a separate value and then separately a proof about that value, and we constantly have to keep those two in sync, we could instead just say this function BST insert actually takes as an argument a binary search tree. And it produces, takes as an argument a binary search tree and produces as an output a binary search tree. And every step in the recursion, of course, you still have to set up that proof that what you've constructed as a valid binary search tree. But effectively, this function now packages together the proof and the value. And so you no longer separately have a program and separately have a verification of the program. Like you don't separately have the program and then separately a verification condition that you've generated for that program that Z3 is verified. You've actually got one piece of code that does both at the same time. Does that answer the question? Does that help?
Yeah, that helps.
So
I was nodding,
you know,
but I realized that's not really
yeah, it doesn't work in
productive
this,
at the
in this
moment.
medium. Yeah, the nodding doesn't work. So basically, you know, this is sort of a different style, a different approach to writing down a program to be verified that intermixes the verification and the program portion as much as possible. And to the extent that those share a lot of structure, this can be a big win for a large program. So sort of to sum up this idea of like, what have we learned about dependent types? Why would you use them? Basically, it looks like I had a slide to answer Skylar, but it wasn't a planted question. Basically, my answer is that dependent types allow us to write down a program that computes both with values and with proofs. So it sort of packages together the value and the proof. It's one program, one piece of code that does both, as opposed to two separate pieces that you're trying to keep in sync. And in some sense, you can think of this as being, you know, ordinarily we first write a program and then later we verify it to be correct. And in that sense, in that case, it might make sense to think of the program and the verification as being two separate objects, because you made one first and then you made the other later. But if your goal is to produce a verified library, dependent types are an attractive approach because they incorporate the value and the proof together and force you to construct both at the same time. So if you want to write down this kind of dependent types world, there's not really that much you have to do. The core language is based on very few primitives, basically inductive types and functions and some core propositions that you might be interested in defining, like and or. And this sort of approach, this is being increasingly used in academia and also to some extent in industry. And we're going to see an example of that in our next class. So on Thursday, I'll be walking through a paper that implements a very fast cryptography library, while also proving a bunch of useful facts about that cryptography library, like that it's correct, in a dependently typed language, like what we've been talking about. So what I'd like you to do for next time is to actually look over that paper. Reading a paper can be intimidating the first time you do it, but if you scroll down to the bottom here, you see a link to the paper. Hope it works. It does. And in particular, start off by reading this abstract, which is fairly short, and this motivation section, which is about a page and a half long. And that'll give you some idea of why did the authors of this work, namely Adam Chapala at MIT and a bunch of his students, why did they choose this approach to implementing a fast cryptography library, and what kind of results did they get? So in fact, they've been able to construct a cryptography library that's as fast as a lot of existing ones, but also required way less sort of cryptography expertise to implement well. And they've even done cool things with that ability, like search for novel crypto systems that no one had implemented before and test how well they would work. So that'll be sort of basically the very end of the class. We'll have one more class after that, looking at a conclusion for the whole course, but that should give you sort of a sum up of, in what cases would you use this dependent types approach and what value might it have? And of course, I know that you're also working on class projects, and as always, please fill out the course feedback form. It is on the website linked. Well, it will be linked in just a moment. I'll put that up. And stand by, you're at your computers already. I don't want to lose the moment. Okay, that should be online in a second. So if you could all fill out the course feedback as is usual, and then if you could, and then just continue working on the class projects and take a look at that paper before Thursday's lecture as well. So I'm happy to take any questions at all. And other than that, I will see you on Thursday. and the feedback form is up, so please fill it out.
When are the final presentations due, like relative to the lecture? Because we're not presenting them in the lecture, right? That would take too long.
Yeah, we're not presenting them in the lecture because of the sort of time loss due to the crazy stuff that's going on in the rest of the world around us. Just to review how the final presentations are going to work, and this should be on Canvas as well. I'm asking you to upload those presentations by end of day Thursday. End of day being the minute before midnight. I'm asking you to upload a recording of yourself giving that final presentation, or of your project group if it's a group. These presentations are twice as long as the milestone presentation. So if it's solo, you have 8 minutes. Think of that as 7.5 minutes, I guess. And if it's a group project, you have 16 minutes. And I'm also asking that these final presentations are also standalone presentations, and that's why you have more time. So I'm asking you to introduce the whole project that you're doing, including any background we might need, any design decisions you make, then talk about how you implemented the various phases of your project. And it's up to you if you want to talk about how you've changed your approach over time, or if you just want to present sort of the final result. I'm also asking you to focus in this final presentation on evaluating the result. So if you're doing a group project, then you have to come up with some project specific idea, notion of evaluation. If you're doing the solo project, I'm basically asking you to say, what programs have you attempted to verify? How have you looked for bugs in the implementation you have? Have you made sure that you can verify incorrect programs? Or if you can, what are the limitations to your proof approach? And of course, have you made sure that you implemented a correct quicksort algorithm and correctly verified it? So that's what's in that presentation.
Thanks.
Other questions? Well, I'll see you all Thursday. I mean, you can hang around and ask more questions if you have them, but go ahead, Sayamshi.
Do we have to submit the code also by 16th?
Yes, I'm asking you to submit the code by the 16th as well.
So both the code and the presentation, we have to zip it up and submit on Canvas.
So there's two separate Canvas assignments. I think I set that up. One for the code and one for the presentation. So with the code, we'll basically be poking around the code to check that you've actually implemented what looks like the whole assignment, seeing that you did it in something approximating a sane way, and we might try to get your the resulting code up and running a little bit and see does it actually verify quicksort? Can we break it by asking it to verify something false? That kind of thing.
Okay, cool.
So there aren't like, this does not have to be the world's best code. We're not going to take points off for using the wrong variable name or not having enough comments, that kind of thing. Maybe if you have too many comments. No. We won't take points off for that kind of thing. But we're asking you to upload the code because, I mean, we need to check that like you did it, right?
Good. Okay. Thanks.
Any other questions? Not really anyone around to ask the questions, but if you all have any, please go ahead.